Hey guys, welcome to another lecture video for Chem 104. In this video, we will discuss factors that affect the solubility of solutes and solvent. So the three factors that we're going to discuss is the polarity of the molecules, the temperature, and the pressure. So we're going to go ahead and discuss how polarity of the molecules can affect the solubility of a solute in solvent. So let's imagine that we have this beaker of water, and we're looking at the beaker at the very top. Let's just say that we have this solute and its identity is going to be AB. And so this is not an actual chemical formula. It is just representing a random solute that we currently don't care of its identity for now. So let's just say that this solute just somehow is colored, and its color is yellow. And so when we place this colored solute, let me write that down over here, inside this beaker filled with water, if this solute is able to easily dissolve into the solvent, then the color of the solution is going to turn green. And so yellow and blue makes green. And so if we have a homogeneous solution such that we don't really see a separation of layers between solute and solvent, everything is evenly mixed, if you will. And another a term for that is miscible. And so if our solute is miscible in this current solvent, then all of the particles of AB will evenly distribute itself throughout this beaker. Now, if we have another solute, let's just call it CD, and let's just go ahead and keep with our color, with our current color coding. And so let's just say that this molecule or this solute CD is colored yellow. If we place it in the solution, and if it does not dissolve inside this solvent of water, what we're going to see is a separation of layers, such that we see a layer at the very top that represents the solute that we just added. And so notice how this second beaker will not turn green. Rather, we will see two different colors to represent a heterogeneous solution. And so if our solute does not dissolve in this solvent, and we form a heterogeneous solution, then we would say that the solute is immiscible in solvent, in the current solvent that it's at. So right now the common solvent that we're using is water, but there are lots of other solvents that we can use. And so what we're going to discuss is how polarity plays a role in determining whether or not the solute is miscible in solvent or immiscible in solvent. And so since we're talking about the polarity of molecules, we have to kind of fall back on the idea of Lewis structures. And if you guys are given a compound, an actual chemical formula, you should be able to write or draw its Lewis structure. And from its Lewis structure, you should be able to determine whether or not the molecule is polar or nonpolar. And so it turns out that for solutes to be miscible, in solvent, its polarity must be similar to the solvent. And so if a solvent is polar in character, and if you put in a polar solute inside that same beaker, then you can expect that those two compounds will be miscible, forming a homogeneous solution. However, if your solute has the opposite polarity of its solvent, in other words, if the solvent is polar and the solute is nonpolar, then it shouldn't surprise us to see a heterogeneous solution form. And so the idea of like dissolves like is going to be our driving force to explain how polarity of the molecules, polarity of the solute allow it to be dissolved or not dissolved in solvent. Okay. And so this phrase, like dissolves like, basically describes that if your solute is polar in character, and if your solvent is also polar in character, then you should see a homogeneous solution. In other words, it's miscible. The solute is miscible in the current solvent that it was put in. Okay. And so if our solute and solvent is nonpolar in character, we would then expect to see the very same outcome as the first. In other words, we're going to form a homogeneous solution. And once again, homogeneous solution basically means that both the solute and the solvent are equally distributed throughout that container or throughout the solution. Now, if your solute and solvent, Now, if your solute and solvent have opposite polarities, in other words, one is polar and the other one is nonpolar, or vice versa, since you have opposite polarities, if you will, it's most likely that you will form a heterogeneous solution. Because the differences in polarity between solute and solvent does not allow both of those molecules to interact through intermolecular forces. Okay. And so that's the main driving force of this specific topic. And what we're going to do is we are going to work through some examples to kind of bring home the point. So what we're going to address is which type of solvent, let's just say H2O versus CCl4 for now, carbon tetrachloride, would be used to dissolve the following solutes. And so the first example that we're going to do is pH 3. So this is phosphorus Tri Hydride. And so before we determine the polarity of pH 3, let's go ahead and determine the polarity of H2O and CCl4. And so to do that, we're going to go ahead and draw Lewis structures. Now, I'm not going to go through the steps to draw the Lewis structures. I'm just going to go ahead and draw the result, the final Lewis structure for each of this compound. And so this is the Lewis structure of water. And if we draw the Lewis structure for CCl4, we're basically going to have 4 chlorines surrounding the carbon. And I'm going to go ahead and draw the lone pairs on the chlorine. And so these two Lewis structures that I just drew, they are going to represent the solvent that we're going to start putting these solutes in. And so for us to determine if this solute, pH 3, is going to dissolve in water or CCl4, we need to understand the polarity of each of these molecules. And so since the central atom of water, which is oxygen, contains lone pairs, automatically water is going to be polar in character. If we look at CCl4, notice all of the surrounding atoms are symmetrical. They're all chlorines. In addition, notice that this central atom carbon, does not have a lone pair. And so even though chlorine, the surrounding atoms of chlorine, does have lone pair, since it's not on the central atom, we're going to disregard it in terms of polarity. And so since the central atom does not have any lone pairs, and since all of the attachments to it, if you will, are all the same element, then we can go ahead and say with a strong conclusion that CCl4 is nonpolar in character. And so now that we've determined the polarity of the solvent, let's go ahead and determine the polarity of the solute. And so once again, we're going to go ahead and draw the Lewis structure for pH 3. And I'm just going to go ahead and draw the results. And so if this is the Lewis structure of pH 3, notice that there is a lone pair on the central atom, which is phosphorus in this case. And if that central atom does have a lone pair, it automatically makes this molecule polar. So now that we've determined the polarity of this solute, and we've determined the polarity of the solvent, which of the two solvents do you think pH 3 can be dissolved in to form a homogeneous mixture or homogeneous solution? And so if you had said water, then you're correct. If you put pH 3 in a beaker filled with water, we would be we would expect that both compounds would be miscible, forming a homogeneous solution. Okay? So hopefully that explanation makes sense. Let's go ahead and do another one. Let's go ahead and do CH3Cl. So we're going to determine if CH3Cl can be dissolved in either water or carbon tetrachloride, CCl4. And we're not really changing the identity of the solvent. It's still going to be the same. So therefore, we can go ahead and assume that water is polar in character and CCl4 is going to be non-polar in character. So this guy is polar and this is non-polar. And so if we draw the Lewis structure for CH3Cl, the carbon is going to be our central atom, and it's going to be surrounded by the 3 hydrogens and the singular chlorine. It doesn't really matter how you guys place your chlorines and hydrogens. All it matters is that they're all surrounding the carbon. There are very specific rules to drawing Lewis structures, and I do encourage you to go back and review that section in your book, because you really do need this skill once again to be able to answer these questions. Now, if you look at the central atom for this Lewis structure, it's carbon. And the central atom does not have any lone pairs. And so, therefore, we have to look at the surrounding atoms, such as hydrogen and chlorine, to determine whether or not this molecule is polar or nonpolar. Now, notice that these 3 atoms are hydrogen. However, the 4th atom is chlorine. Since there is asymmetry in the identity of the surrounding atoms to the central element or the central atom, then we can go ahead and say that this molecule is polar without having to calculate the Pauling numbers and determining the dipole moments and all of that stuff. And so we're just using 2 simple criterias to determine if a molecule is polar or nonpolar. Since we have asymmetry in the surrounding atoms, or the atoms that's covalently bonded to the central atom, and since we don't see any lone pairs on the central atom, which is carbon in this case, we're going to go ahead and conclude that this molecule is polar. And so if we wanted to create a solution that is heterogeneous or immiscible, where are we going to dissolve CH3Cl in? Will we dissolve it in water or CCl4? And so if you answered CCl4, then you are correct. Once again, I'll go ahead and write the question. If we wanted to make, okay. And so if we wanted to make a heterogeneous solution, what solvent will we use if we have these 3 compounds? And so since CH3Cl is polar, and since CCl4 is nonpolar, placing those 2 compounds in the same beaker will form an heterogeneous solution, so they are immiscible. They will not be able to dissolve with each other and therefore create two solutions. One layer will represent CH3Cl and the other layer is going to represent CCl4. As to which compound goes to the top and which compound goes to the bottom, it depends on their density. All right. So hopefully you guys are kind of understanding the train of thought with respect to polarity of molecules, affecting the ability for a solute to be dissolved or not dissolved in solvent. So let's go ahead and do a couple more examples. So let's just do H2S. And we're going to determine whether or not H2S can dissolve in water or CCl4. So once again, water is polar and CCl4 is nonpolar. And so if we draw the Lewis structure for H2S, and if we draw it correctly, we'll probably be able to determine whether or not it's polar or nonpolar. And so it turns out that H2S will have a bent structure, and it will have two lone pairs on the central atom. Since there are lone pairs present on the central atom, then we can go ahead and say that this molecule is polar. So if we wanted to dissolve H2S in a specific solvent to form a homogeneous solution, which solvent do you think we will use? So if you said water, then you are correct. Since water is polar, and since this molecule is also polar, then if you put them together inside a beaker, then you get a homogeneous solution. In other words, these two compounds are miscible with respect to each other. All right. And so let's go ahead and go through another example. Let's put in KCl. So KCl is potassium chloride, and we're still going to answer the same question. Which solvent will KCl be dissolved in? Either H2O or CCl4. Okay. So I'm just going to put that reminder that water is polar and CCl4 is nonpolar. Now, if you look at the compound that we have, KCl, since K, or potassium, is a metal, and Cl is a nonmetal, what we have here is an ionic compound. And when we have an ionic compound, we don't use the rules to determine the Lewis structures. We just know that KCl will be dissolved to produce K plus and Cl minus. And so this is a full positive, full negative charge. So since these ions have a charge to them, it would make sense for these ions to interact with a solvent that also has some type of charge to it. And that would be water. And so when we draw the Lewis structure of water, we did conclude that because there are two lone pairs on the central atom, that this molecule is polar. But if you guys are looking at dipole moments, the partial positive and partial negative charges on this molecule, since oxygen is our most electronegative atom, we're going to have a dipole moment pointing towards oxygen, where there's going to be a partial negative charge and a partial positive charge. And so since these ions have a negative charge, it's the chloride is primarily going to interact with a partial positive charge of water. And the potassium, since it has a positive charge, it's probably going to interact with the partial negative charge that's on oxygen. And so because those two are interacting through an ion dipole intermolecular force, they'll still be able to dissolve amongst each other. Okay. And so we're going to go ahead and look at one final example, which is CO2. And we're still going to ask ourselves the same question. Which solvent will CO2 dissolve in? H2O or CCl4? Now, if you look at the identity of the elements inside this compound, CO2, they're all non-metals. And so this is a molecular compound, indicating that we could probably draw its Lewis structure to determine whether or not it's polar or non-polar. Okay, so I'm just going to put a note that says all nonmetals. And all nonmetals are molecular compounds. And molecular compounds, if you recall from the previous lecture videos, the bonding is going to be covalent. And if the bonding is covalent, then we can go ahead and apply the rules of Lewis structure to it, to draw it. And so I'm just going to go ahead and draw the final outcome of CO2, the Lewis structure of CO2. And so if you look at the central atom, which again is carbon, there are no lone pairs, so it could be nonpolar. But we also want to check the identity of these surrounding atoms. And since they're both oxygens, they're both symmetrical, right? And so since it has no lone pairs and because its surrounding atoms are the same, then therefore we can conclude that CO2 is nonpolar. So if we wanted to create a homogeneous solution, which of these two solvents will we use to create this homogeneous solution? And so if you had said CCl4, then you are correct. And so remember, CCl4 is nonpolar. And so nonpolar will dissolve other compounds that are nonpolar, forming a homogeneous solution. Cool. And so hopefully you guys understand how polarity of molecules allow solutes to be dissolved or not dissolved in a specific solvent. Next, we're going to go ahead and discuss how temperature affects the solubility of solutes inside a solvent. And for that, I'm going to go ahead and use my lecture slide. And so if we wanted to understand how temperature affects the solubility of specific solvents, we're going to go ahead and look at this chart. So I'm going to quickly zoom in. And so on the y-axis, it's describing the general solubility, and it's expressing it, it's quantifying it in terms of grams of solute per 100 grams of water. And so if you look at the x-axis, the temperature is increasing from left to right. And so this is telling us that as we increase temperature, will the solubility increase or decrease? And so we're going to go ahead and follow one specific ion. Let's just say potassium iodide. And we're going to start from 0 degrees Celsius, and we're going to work our way towards the right. And so as we increase the temperature, right, as we go from 0 to 20, 20 to 40, 40 to 60, notice that we're increasing the solubility of that compound as temperature increases. And we can go ahead and observe that trend, that same trend, for other solutes. And so the question that we want to ask is why? Why does increasing the temperature increase the solubility for these ionic salts? And so we have to think about temperature in the sense of, in the perspective of kinetic energy. And so if you guys if there is if the temperature of this beaker, let's just say for example, is 0 degrees Celsius, then in terms of kinetic energy, these water molecules are not going to be moving a whole lot, right? So they're probably just going to move around and slightly bump each other, and they'll be okay with it. However, as we increase the temperature to, for example, 30 degrees Celsius, and this is just a random number that I'm spewing out. As we increase the temperature, what happens is that we're increasing the kinetic energy. So I'm going to abbreviate kinetic energy as Ke. We're increasing the kinetic energy of the water molecules such that the water molecules are now colliding with a solute at a higher rate. And if these water molecules and the solutes are colliding amongst each other at a higher rate, then it's going to break up all of these solids, so to speak. Or it's going to break up these solid crystals into individual pieces, allowing the solute crystal to be dissolved at a higher temperature. Cool. So hopefully that makes sense. So overall, we can say that the solubility increases when the temperature of the system increases. And the underlying factor is this increase in kinetic energy. The idea that these water molecules are colliding with the solutes at a higher rate, thereby breaking up the little chunks of, if you will, of the crystals into individual components that we as humans can no longer see. Okay. And so let's go ahead and talk about temperature once again. However, we're going to, instead of ionic solids, like what we discussed in this slide, we're going to go ahead and discuss how temperature affects the solubility of gases. And once again, we're going to go ahead and look at this chart. So if you look at the x-axis, we see an increase in temperature going from left to right. And on the y-axis, once again, it's describing the solubility. And we'll talk about how solubility is quantified in another lecture video. And so if we follow this trend, let's just say oxygen. And so if you kind of extrapolate that value of x here, so we can roughly generally say that at 5 degrees Celsius, oxygen has a solubility that's close to 2. Okay, maybe like 1.98. But as we start increasing the temperature, as we go from 5 to 10 and 10 to 20 or 20 to 30, and if we follow the line, notice how the solubility of oxygen is decreasing. So in this scenario, there's going to be an inverse relationship between temperature and the solubility of gases. Whereas for ionic solids, there's a direct relationship or a proportional relationship. So let me just write that down. So there's going to be an inverse relationship between solubility of gases and temperature. And so what we want to do is we want to understand the reason why. And for us to do that, we're going to go ahead and take a look at this diagram on the right-hand side. And so let's just say that these purple spheres are representing a gas molecule. It doesn't really matter what gas molecule it is. All we know is that it can. All we need to know is that it can enter the gas phase. And so when we're adding heat to the system, what we're doing is we're once again transferring kinetic energy to these individual molecules. And if these individual molecules are gases, they now have a high enough kinetic energy for them to break all the intermolecular forces that's holding it inside the solution so that it can escape and it can become gaseous in phase. And so I guess this is something that you may have already encountered but not realized. Let's just say that you guys are out with your family or friends, you guys are by the beach, and it's a hot summer day. You take out, a soda can or a soda bottle, and you open it and you leave the cap open. And as the day progresses, the afternoon gets hotter and hotter and hotter. And all of a sudden, when you drink that soda can or that soda bottle, you perceive the soda to be flat. In other words, there's no carbonation. And so the reason why is because the extra, as the afternoon gets hotter and hotter, that kinetic energy is going to be absorbed by the carbon dioxide that's inside your drink. And so that CO2, when it absorbs enough kinetic energy, it allows that CO2 to basically, once again, break all of the intermolecular forces that's holding it inside the solution, that's holding it in the solution, and thereby enabling it to become gaseous in phase. And so basically your CO2 is just going to fizz, it's just going to fizz away. And so overall, the solubility of gas molecules dissolved in liquid is going to decrease if you increase the temperature of the system. And so, there's a lot of discussion about global warming and other, global effects, human footprint, and all of that stuff. And so if you think about it, if you increase the global temperature even by a few degrees, it's going to decrease the solubility of oxygen in, for example, our oceans, our lakes, and our rivers, where certain organisms rely on that oxygen to basically to quote unquote breathe, and more so on a biochemical level, use that oxygen to drive oxidative phosphorylation to create biological energy in the form of ATP. And so, even increasing the global temperature by a few degrees Celsius, it affects our smallest organism, because then the solubility of oxygen is going to decrease. So there's less resource for a specific, number of microorganisms or organisms just in general to utilize that oxygen to drive on a cellular level the production of ATP. And so the last thing that we're going to discuss is the effect of pressure. So it's another gas related concept that relies on solubility. So we're going to go ahead and discuss the effect of pressure on solubility. So for gases dissolved in solution, we want to understand how increasing or decreasing the pressure affects the solubility of the gases. And so let's go ahead and take a look at this container. So this container on the left-hand side is going to exert a constant pressure on these gases. And so let's just say that its current pressure is 1 atmosphere. And so what happens is that when you increase the pressure, so let's just say we'll double the pressure, so let's just say 2 atmospheres. If we're increasing the pressure, notice that these molecules, they have less volume to occupy. And so what's going to happen is that a small fraction of the molecules that were gaseous in phase, when you increase the pressure, you're going to force it to be dissolved in the solution. And so overall, as we increase the pressure, we are increasing the solubility of gas in liquid solution. And we can go ahead and see that trend by looking at this graph. So if you look on the x-axis, we have partial pressure. So don't worry about the word partial for now. Let's just focus on pressure. And so if we increase the pressure from left to right, how will the solubility be affected? And so if we're following, for example, helium, at 0 atmosphere, it has 0 solubility. However, if we increase the pressure, notice how the slope increases. And so since there's an increase in the slope, there's also an increase in the solubility. So for example, at this amount of atmospheric pressure, it has this amount of solubility. However, at 1 atmosphere pressure, notice how the solubility is now higher when the pressure increases. And so this is something that's actually been taken advantage of in terms of industry. And so this is the reason why I put a little soda can up here. And so one of the ways that your soda becomes fizzy is by increasing the pressure of the system. So, for example, if you wanted to make your own soda, you're going to go ahead and take some sugary beverage that you like, and then you're going to go ahead and pressurize the system such that you're forcing the gas molecules, specifically CO2, to be dissolved in solution. And so once that system has been pressurized, there's going to be a lot of CO2 that's going to be dissolved in solvent that it would not necessarily, it wouldn't necessarily dissolve naturally. And so when you pop open the can, so when you open your drink, you hear that fizzy sound. And that fizzy sound basically is a release of pressure. And releasing that pressure allows the excess CO2 molecules that's been forced to dissolve in the solution to now enter the gas phase, allowing it to escape. And when you're drinking this carbonated beverage, you're feeling that bubbly feeling down your throat. And that's because you have all of these carbon dioxide molecules that's basically entering the gas phase. It's losing its solubility to be dissolved in solution. Okay, and so we've discussed the different factors that affects the solubility of solute inside solvents. So we talked about polarity, we talked about temperature, and we talked about pressure. So the next thing that we're going to discuss is quantifying solutions. So we'll talk about concentration. All right, guys, I'll see you in another video.